Hey everyone, welcome back, and today let's solve Leetcode problem 2064 titled Minimize Maximum of Products Distributed to Any Store. So we're given an integer n indicating that there are n specialty retail stores. There are also m product types of varying amounts which are given also as a zero indexed integer array quantities, where quantities at any index I is going to represent the number of products of the ith product type. Pretty straightforward. So we need to distribute all of the products to the retail stores following the following rules. So the first criteria says that a store can only be given at most one product type, but can be given any amount of it. And after distribution, each store will have been given some number of products, possibly zero. And we need to let x represent the maximum number of products given to any store, and we want x to be as small as possible. So basically we want to minimize the maximum number of products that are given to any store, and we need to return the minimum possible x. Hence the name minimized maximum of the products distributed to any store, right? So we're not actually given an array of all the different stores. We're simply just given n, which is going to tell us how many different stores we actually have for that example. So in example 1, we have our input n to be 6, meaning we have 6 stores and we have 2 different products in our quantities array, one of quantity 11 and one of quantity 6. And we need to minimize the maximum amount of products in one store. Okay, or rather distributed to one store. Okay, so in this case, we have an output of 3. That is the minimum maximum. But why is that? Why is that the way? Well, one optimal way we could do this to get that minimized maximum of all the different stores to be 3 is the 11 products of type 0 are going to be distributed to the first 4 stores in these amounts, right? They're going to have 2, 3, 3, and 3. And the 6 products of type 1 are distributed to the other 2 stores, which would be 3 and 3. And note that the maximum amount of products in any store is at most 3. And that is going to be the value that we output. All right, we're trying to minimize that maximum. In this case, the maximum is 3, and that is as small as we can make it to be. And as you can see, the maximum number of products given to any store is the max of, again, 2 and all these 3s of all the different stores we have. In this case, that's 3, and so that would be the value it up, but the minimized maximum. In example 2, we have our input n to be 7. We have 7 stores and 3 different products of 3 different types in our quantities array of quantity 15, quantity 10, and another product with quantity 10. In this case, we output 5. Why is that? Because one optimal way to minimize the maximum number of products in all the stores, of, in this case 7, is going to be the 15 products of type 0, the first, or rather 0th index in our quantities array, can be distributed to the first 3 stores in these amounts. 5 for the first, 5 for the second, and the last 5 for the third. And the 10 products of type 1 can be distributed to the next 2 stores in these amounts, 5 and 5. And finally, the 10 products of type 2, the last 10 products, can be distributed to the last 2 stores in these amounts, 5 and 5. And if we actually take the maximum of all the number of different products in all the number of different stores, we see that it's just going to be 5 because we have exactly 5 products in each store. And so we'd output 5. And that is actually the smallest number of products we can actually have as the maximum for any of them in the number of stores that we actually have. And finally, in example 3, we have our input n to be 1. We have only one store, and we also only have one quantity. In this case, it's going to be 100,000, and obviously we simply only output 100,000 because there really is only one optimal way. It's the only one, and that's going to be all the 100,000 products of type 0 are distributed to the only store that we have, the only one store, and so the maximum number of products would be the maximum of just 100,000, and that's just 100,000, right? We have no other possible ways to distribute these products because we only have one store to do so. So, with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so to actually solve this problem efficiently, we're going to use a binary search algorithm. It's probably well known. You guys probably know this as well. And we're going to do this to actually find the minimized maximum number of all the different products in a single store. Okay, so to do this, we'll actually have an initial helper function. I don't know, I'll just call it distribute or whatever. And it's going to check if a certain maximum is actually possible to achieve or feasible by determining the number of stores required to distribute the products without exceeding the maximum. And for the actual binary search part of our algorithm, we're going to perform that binary search on the possible values of the maximum number of products per store and adjust our bounds or our 2 pointers based on the feasibility using that helper function. So let's just go ahead and dive straight into the code here. I'm actually going to directly kind of just define my helper function here. I'm going to call it can distribute here. Can distribute. I think that's how you spell it. Should be right. And for our parameters, I'm simply just going to take a max products. Max products. Okay, so what is the real functionality of this helper function? We have one parameter, max products, and if you really want, I can type in this. It's going to be of type int or integer, and it's going to output a value of a boolean. Okay, simply just checking if we can actually distribute this of the max products. Okay, well, we have one argument. Great, we're going to output a boolean, which is going to represent the maximum number of products that we actually want to test for each store, right? And it's simply going to return that boolean value true if it's possible to distribute the items with this max products limit across all of our n stores, right? Otherwise, we'll simply return false. Okay, so once we've defined that helper function, now we'll just initialize our first variable within this function, stores needed. And quick note here, since this is actually a nested function within our main function of minimize maximum, we don't actually have to again pass in the parameters n and quantities. They're already kind of assumed to be parameters in this function because it's nested, right? We already have access to these variables, or rather inputs, okay? So we'll have stores needed initialized to be 0. And what is this going to do? Well, it's simply going to keep track of the number of stores that we'd actually need to distribute all of the products to different stores without actually exceeding that maximum products limit. Okay, so once we actually instantiated that variable, now let's loop through all of our quantities. So for quantity in our quantities input array. Sorry, I really can't spell today. And they gave us such advanced vocabulary words in this problem, whatever. Okay, so we'll just iterate over all the different quantities in our quantities product array. Okay, and we're going to increment our stores needed plus equals, what are we going to do? It's going to be, okay, sorry, I don't know why I have one there. It's going to be the quantity plus the max products minus 1. And then once we have that, it's going to be divided by the actual max products themselves. And I think, yeah, okay, I have this in parentheses, divided, integer division, by the max products. Right? We're simply just having kind of ceiling division. Okay, well, that's nice. We have all of that. Why are we doing this? Why are we having this ceiling division? Well, for each quantity, we have to actually calculate the number of stores required to distribute that product type without actually exceeding those max products per store. And the formula here that we actually use, quantity plus the max products minus 1, integer division by max products, is actually a ceiling division that's going to tell us how many stores are actually needed for that specific quantity that we're currently iterating at, this whatever quantity we have, whether it be 15, 10, or whatever value it is in our example for our input array quantities. Okay, and we actually have to add that corresponding value here, right, the number of stores required to distribute this product type or quantity type throughout all the stores, and actually add that to our stores needed, right? Basically just incrementing this stores needed variable based on how many stores are required for this current quality product. So once we've done that, now we have to actually check, okay, well, if these stores needed, if that's actually greater than n, we have to immediately return false. Why is that? Why if it's greater than n? Well, basically, if it exceeds the number of available stores, which is given by n, then we can't really actually distribute the products with the current max products limit, and so we have to immediately return false, right? However, if that's not the case, then we can return true if we don't return false and enter in that conditional, right? If the loop actually completes without the stores needed exceeding n, that means that the distribution is actually feasible with the given max products limit, and so we can return true. Okay, alrighty. Now, so once we've actually had that and returned that Boolean value, now let's actually initialize our binary search. Okay, so we'll have left and right to be equal to the bounds of our search range. So it's going to be initialized to 1 and the maximum of our quantities array. Right, again, these are just our actual binary search bounds. All right, we're just going back to our main function and setting up these bounds, right? And left is set to 1. Why is left 1? Well, that's going to be the minimum possible value for the max products per store. We can't distribute less than at least one product or one quantity for each store. We have to at least have one, right? That's going to be the minimum or leftmost boundary in our binary search range. And our right is going to be set to our rightmost boundary. It's going to be the maximum of the quantities. Why? It's going to represent the maximum possible value if only one store had to take the largest product quantity. So, per se, in our 6 stores in example 1, if we gave 11 products in this first quantity index to one store, well, immediately we'd output 11, right? That's the maximum one store could potentially have. We can't have 12, we can't have 13 because we don't even have that many products for it to be a potential maximum. And so the maximum of our quantities input array of the number of products we have is going to be our rightmost boundary, right? If only one store had to actually have the largest product quantity in that input. Okay. So now, like we usually do for binary search, while our left pointer is in bounds of the right one, it's less than strictly the right one, right? So while that's true, we can continue our while loop to actually help us narrow down our search for that minimize maximum like we usually do for binary search algorithms. We're going to initialize our middle, you've probably seen this a million times, equal to left plus right divided by 2, the definition of a middle index. Okay, once we've initialized that middle index, right, to actually represent a possible candidate for that max products that we have to actually check if it's feasible to achieve or not, now we actually have to check, well, if can distribute, okay, I'm having a trouble spelling this, I think this should be right, can distribute, yeah, okay, so if can distribute, okay, so we're simply just having kind of like a feasibility check, right, using that can distribute helper function, right? And we're calling this helper function with our middle. Oh, oops. Literally forgot to pass in my parameter. Okay, middle. Okay. So we're just calling this actual can distribute function with our middle as the parameter to check, well, is this midpoint that we're currently defined for this iteration, is it actually feasible as the maximum number of products for the number of stores that we have? And if this is true, in that case, then we can set right to be equal to mid. Why is that? If it's true, then it means it is actually feasible to use mid as the maximum, and so we can update our rightmost boundary to be minimum, or to be mid. Why is that? Because that lets us check even smaller maximums in the next iteration of this while loop, because we know that this middle is already feasible. It's already true for this helper function. It already does work. So we can set update right to be mid to explore the left part or left half of our search range. However, if this is false, well, we have to increment our left, or rather update our left, to be equal to mid plus 1, right? Pretty standard. Why is this? That means mid is too small. It's not feasible just yet. It's way too small of a value, and so we have to adjust left to mid plus 1 to actually increase the minimum bound for this current range of our binary search, right? To actually look in the right half of our binary search range. And effectively, we simply have to return left outside of this while loop once we're done iterating through all the different search ranges while left is in bounds or less than right? And why is that? Because left is going to be at that minimized value. It's going to be the leftmost bound in that search range that actually allows this distribution to be feasible. And so we can simply return left. It's going to be the smallest possible value of a maximum that we can actually distribute different products to different stores, right? The leftmost boundary of our feasible search range, right? The minimized maximum. And so unless I made any syntax errors here, this should be accepted, and this should be a valid solution. Okay, let's see what I did wrong here. Oh, oops. This should be indented within our can distribute function. Sorry about that, guys. All right. Now this should work. Sorry about that quick syntax error here. And as you can see, this is just about as efficient as you can get. So to quickly reiterate what this code does overall, I'll try to give you a high-level explanation. So, okay, we're simply using our standard binary search algorithm to actually find the smallest possible maximum number of products that any single store will need to hold, right? And we do this by actually testing midpoints using that mid variable of our search range and adjusting our search bounds based on whether that distribution is feasible, and we can check that using our helper function to check if our number of stores needed for that current product or store, if it's actually greater than n, or rather less than n, then we can return true, meaning it's feasible for that value, okay, for that middle value that we kind of define, right? And we're simply checking if it's actually valid with each distribution, if it's feasible with each midpoint mid, okay? And we simply have to return left. Why? Again, because that's going to be the minimized maximum value, or the leftmost bound of our valid or feasible search range. So for the time complexity of this solution, this is going to be a big O of m times the log of the max of quantities. Why? Because m is going to be the length of the quantities, and our binary search is actually going to run in big O of log of the max of the quantities, right? We want the actual max of the quantities because that's going to be kind of our search boundary, or our search range boundary. And let me actually comment this out because it might be a little bit hard to understand. So time complexity, this is going to be big O of, okay, it's going to be pretty tough to write here, big O of m times the log of the maximum value of our quantities input array. And why is that? Because, of course, the binary solution actually is part of our solution is going to run in big O of log of the max of quantities, and we're actually checking for each midpoint by iterating over the quantities as well in that kind of check using that can distribute mid function. And so for that reason, that's also going to be a big O of n kind of big O of m kind of operation, right? It's going to be a linear operation. That's going to be big O of m, the linear portion, times the log of the maximum value of our quantities. Okay, and for space or memory complexity here, really can't spell today, it's going to be big O of, well, 1. It's a constant time solution. It's just about as efficient as you can get. Why? Because we're not actually using any auxiliary memory here or any extra data structures to store any elements from our input. We're really only using some kind of integer variables, right? Like left and right, like mid, like things like that, like stores needed. And we're not actually using any extra data structures to actually solve this problem, right? In other words, we're only using a fixed amount of extra space, a constant amount of extra space for variables that don't require any extra data structures. What does that mean? The amount of memory that we actually use in our RAM, right? In other words, the number of data structures that we actually use do not grow with our input size. So even if our input becomes massive, we're not using any extra data structures. We're using fixed variables. We have like 3 or 4 fixed integer variables regardless of how large our input size gets. And so for that reason, this is going to be a big O of 1, or constant time memory solution. So with that out of the way, if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel, and I'll see you guys in the next video. Bye-bye.